Okay. Yeah. So based on what I assume we already know, like we've done the machine learning side of linear regression, which involves basically classifying, not classifying this time, but predicting data that I won't say like that individual. So for instance, like there's binary classification and all. But the last one which you did was on linear regression. But this time around, we predict individual things, such as classifying tumors. I'll just put this inside. So yeah, so basically what we want to do is to predict discrete values quantity. So which is, for instance, binary classification. Is this person a boy or a girl? More like gender classification. Predicting basically anything that you can actually count discretely. So for instance, there's also the multi-classification side, the multi-class classification, which involves classifying things as individual things, for instance, 1, 2, 3, but not like what you did in the last one, which had like this continuous kind of plots. So a very big example is on breast cancer classification. So it's a well-known one and one of the very popular ones that they tell everyone when you start machine learning, let's try logistic regression. So basically what you want to do is to classify these images as it could be images, it could be information about it, but basically what you want to classify is whether it is benign or malignant. So it's a popular problem, and I guess like they've been much improvement in solving something like this. So basically, it's just a binary classification because you could actually call this benign 0. You could give it the class of 0, and you could give this the class of 1. So whichever you want to do it, but the point is the fact that you're classifying just binary. Yeah, you're classifying it in binary form. Let's give me this, please. Let me show in case of the chat. Okay. Yeah. So if you have any questions, you can drop it on the chat, or you could just like speak. So whichever one is fine. So here's an example of the problem here. This time around, you can see how it's patterned. The blue X refers to the benign, and the red plus refers to the malignant. What we basically want to do is to find how to like separate these two things. So basically, what you can just do, just like the name says, which is logistic regression, you could draw a line to separate both of them. A typical example is what you can see here. We can see this line, the separating boundary. It's called the boundary, which separates the two classes. So at this point, where you can, once you've gotten this optimal line here, what you can literally say is, where you can literally just say is anything that's greater than this line belongs to the malignant class, and anything that is less than this is the benign. Basically, the whole point is that we want to get that optimal parameters that will give us this line. So that's the problem here. I don't know if there's any questions so far, but if you have, you can like just drop it on the comment section or just let me know. There's the comment section, the chat. So here's the normal system of machine learning. Basically, you have your input features. So where X is a vector with n values, then these are basically the features here. Then our output is, for instance, in this case here, we want to predict two things. You could use 0 or 1. Here there is -1 or +1, whichever way, but the point is that you're classifying just two discrete things. In this case, -1 refers to benign and +1 refers to malignant. Now, another important thing to note is that X refers to the features. And basically, there are two features here, which is the mean area and the mean concave points. This one here is reserved for bias. I don't know if you're already familiar with that, but basically, you could call this X0, but the point is that you want a value that way multiplied by the bias. It's still the same thing, it's still the bias, which is 1. So it's not considered, it's not part of the features, but it's part of the setting. So here, our model parameter is theta. So basically what we want is the optimal theta that minimizes the loss. We'll get to that, but we want to find the best theta that gives you the the line that separates the two things we want to classify. Okay, so two things to note here, which is very important. First of all, you have to find this h theta of x. So what this here refers to is basically like the linear combination of your features respect to the linear combination of your features with the weights. So the weights is our theta here. Basically, in vector form or matrices, you have to like transpose this to multiply it by the x. It's kind of like simpler to do this than to add them, like to show them adding. Then here, what you call sign here, this is basically the activation function. So once you've done this linear combination, we need something to like actually let us know, okay, will this thing give us the class malignant or give us the class benign? So that's what this sign is for. There's one that's very popular, which is the perceptron algorithm. Although people don't use it again because of how it works. But basically how it is you just perform a basic check. If this value here, if this linear combination is greater than 0, it belongs to the first class. If it's less than 0, it belongs to the second class. But the issue with this is the fact that you can't really find the optimal values of theta because of its discrete form. So basically, the problem is the fact that it's not differentiable and continuous. So you basically can't perform gradient descent on it. So I think we've spoken about this already. But yeah, something like this here. If it's greater than 0, then it belongs to the other class, that kind of thing.
I have a question, please.
Yeah, sure.
We are moving at an interesting pace. But the like when I was learning this thing, as I didn't understand what they meant by sign. So I don't know, maybe I was just the one that did not know, or maybe people on this call also are feeling like, what is sign? So I want to ask, like, can anyone unmute to explain to us what they understand as the prediction being the sign of the hypothesis function? If you understand already.
I think what it meant is the fact that the sign helps us to put them.
Your voice is very low. Oh, sorry, your audio rather.
If I get him,
Okay.
I'm not sure if I got him right, but what I understood from him was the sign helps us put it into classes based on the sign of our predicted value. So if the sign is a positive, you put it in the positive idea class, and if it is negative, you put it in another class.
Exactly. That's exactly what it means. As simple as that, it can cause you to feel like, what is this? I'm serious. So the sign as it is just what Timothy said it does. Like if the sign of whatever you got from the h theta of x is positive, then you say this is a positive class. You neglect the number. Do you understand? You naturally you get like plus 1 point something or plus 10,000. You don't care about the number, the confidence level. All you care about is it a positive in front of that number or a negative in front of that number, and you just use that as your prediction. So that's what you say your predicted vector would be. Okay, I hope that made it clearer for some of us that probably did not also understand that.
Yeah, thanks. Okay, so at this point here, I don't know if you can remember from the last class. So there's this least square method of finding the actual line that's basically, linear regression uses a linear line to make predictions. So just like in the linear regression side, although this is logistic regression, this was what we used to get the optimal line. So in this case here, even though we're not giving a linear regression, not a linear line for linear regression, we use a line to separate these two classes. So let's just say we have a class that is in this positive side here, and we have another class that is in the negative side. So these two x's are the negative, these 3 x's are in the positive side. So the reason why we can use least square error for this is the fact that if you notice, in the negative side, there are 2 x's here. In the positive side, there are 3. one is kind of like an outlier, although that's where the problem is. But if you see it, it's kind of like far from where these other two are. So, okay. Okay. Do you all remember how linear regression works, basically? I just asked you could say it on the chat. I also want to be sure that we all know what we're talking about here. Like I'd appreciate if someone just like give a very brief overview or like brief summary of how linear regression works and like the objective for it.
Okay, it's a way of doing a classification problem using the linear function. What it does is it finds a line of best fit along which it splits our prediction into two. Would it do this or won't it do it? So he puts a line between the people that would pass or the people that will be on a class. He will put them on one side of the line, and the people that won't, he put them on the other side of the line. And that's what I understand.
Is that linear regression?
Okay, can I speak?
Yeah. Okay. Sure.
Right, Chisholm.
Okay, so basically, linear regression uses will I use a loss function to keep predicting until our y predicted can be as small as the actual y that we have. So in each of the case, the difference is now the line of best fit that we have. So that is the line we call the line of best fit for linear regression. And then it's very differentiation, like it likes differentiation a lot to derive the function for it.
Yeah, you said log loss. Maybe we dial back a little. What loss are we trying to minimize for linear regression?
Okay, the losses are the one between the predicted and the actual.
Yes, we are trying to move closer to the actual. But there is a specific loss that we try to minimize in linear regression. Can anyone recall what that loss is? What is called?
The square loss function.
Yeah, it's it's the very popular one. It's not the only one. Remember, we could also optimize. Yeah, exactly. So I just want us to bring it back so that the more we build, we would see a lot of loss functions, and we need to be able to connect it to the right task we are trying to solve. Timothy said that we are trying to fit a line of best fit, which is correct. But then he mentioned that we want to classify some to be between, it has the ones that the line is trying to classify, ones that are above the line or below the line. I'm not sure, maybe I misunderstood you. I just wanted to.
No, what I mean is we're trying to put that line to separate our data. If you when I read this particular material, there was a slide up there that talks about the benign and the malignant, and then a line just trying to cut it into
You're talking about classification now, right?
Yeah, you're talking about this one. Like I'm talking about the previous one.
Okay. Okay. I think Stanley was asking about linear regression, right? But now I think you're explaining using linear regression for this classification task.
Oh, I understand.
Okay. All right. That completely makes sense. All right.
Sorry, just like 5 minutes. I don't know if you can see this image I have for this simple linear regression. Okay, let me try. I don't know, can you guys see my screen? Like a simple linear regression image.
Yes. Along multiple points.
So there are two different things, even though the fact that they are linear, like I mean both linear regression and logistic regression. So this is how linear regression looks like here. So given these points, which are blue in color, so these are basically our data points here. So what linear regression does is to basically look for the line that fits this data best. So you can see this red line here. This most likely the best line you ever have that fits this kind of data as it says here. So with this, you can literally use that the whole mean square error, least square methods to penalize this point. So you know how machine learning works, unlike we humans, where you can actually just like browse that line by yourself. But machine learning models or computers can't draw this line. So you have to like start from an initial point. It could be any random line anywhere. But basically the whole point is to train it to the point where it will be able to fit this line where it is. So that's where the whole loss function thing comes in. So those loss functions, like the one that Tejus mentioned already, which is like the least square error, the mean square error, and all, you can actually use it to penalize your initial points, comparing them to the actual one. So when you use that, you get your optimal values, your optimal parameters. So that's it for this. So now back to this here. We're trying to see if we could use that same loss function, which is this least squares, for classification problems. But unfortunately, you can't, because it will be affected by things like outliers. So even though X belongs to this, even though it belongs to this class here, it's kind of like far from this. And because of how least square error works, the fact that you're finding the mean, it would drag the line far away from the whole point. Initially, it's meant to classify these two places. That's the negative and the positive side. It's supposed to classify the two sides. But this value, this X here, this data point at the extreme, has like dragged the linear line away from where it's meant to separate them. I don't know if you understand. Like, if you understand, you can let me know or put it on the chat if I continue. If you have any questions, you can ask.
Okay, so I don't really get the green line. Is it like we are going to do the kind of similar thing we did where we were finding E and then we iterate and use the next value of Y and X and then find it again, something like that?
We're still going to do that, but at this point now, what we want to do is to just find a function that is both continuous and differentiable, that penalizes your line, like this boundary. So if you look at it here, we've not gotten to the part we have seen, but what I'm just trying to say is that we're trying to look for a function that would use to penalize your model during training.
So if I can offer some thought here. So Chisholm, imagine that, forget about the green classifier right now. If you wanted to do the same thing we did last week, a linear regression objective, and to do this, your model would most likely come up with this red line to separate it. But it's very clear from what we can see that your model will be misclassifying two of those positive value, has misclassifying the positive. If you said that whatever is above the red line is positive and whatever is below is negative, then you'll be misclassifying one of the positive as negative. Does that make sense?
Yes.
Okay.
Thank you.
So now imagine, this is clearly not right, but it's also possible that you can get the correct classification. Imagine that that's one line in that side, you just delete that data. If you deleted the data, your model will come up with the green classifier. You get what I'm trying to say? And that would be correct, because then you'll be classifying whatever maybe to the right as positive and to the left as negative, and then you would have a perfect classifier. So what I understand Stanley saying is that that least square is being like when there is an outlier in the data or seemingly outlier, then least square can would be performing very poorly. You get what I'm trying to say? If you use this objective, I mean, you can use something better, but if you were like, no, I have to use the least square objective to solve this classification problem, then you might have to look out for your outliers, which is not recommended. Like one would not naturally want to use least square to solve that. But that, does that make sense to you?
Yeah, thank you.
I think Abraham is raising his hand up.
Yeah, thank you so much. I don't know. I just want to maybe make a suggestion also. I don't know if I'm the only one not seeing the cursor move on your screen, but it would have been nice if at least the cursor could point to where you're explaining. Like several times you made mention of the X on the other end, like there are two ends. Yeah, and like
Yes.
this line, this other line, you didn't put the color,
Okay.
like the cursor was moving.
Yeah, it's because I'm not the one sharing my screen. I don't
Not you.
know.
I know, not you. I mean, our instructor for today.
Can you see the cursor now?
Sorry, please,
Hello?
can I ask why are we having outliers?
Why are you having outliers? Because like it's data, like you can't predict how data would look like.
I thought we cleaned the data and it removed outliers.
There are many things that could happen. Like even if this wasn't an outlier, even if we had like two other points here, it still won't work because it would be in between this. I don't know. Can you see my mouse? Can you see my mouse move around now? I'm just be sure.
Your mouse is still not moving on my end. I don't know if I'm the only one.
Yes, moving. I can see it. It's just quite small. That's it.
Not
But
yet.
it's not there. I can see it, but it's
Okay,
just
I
small.
can see it now.
Okay. Yeah.
Yeah.
So
Maybe
what
if you change the color to black. I don't know.
let me see that.
I think it is white too, so
I really don't know how to change this to.
We will
Black.
manage. Don't let's waste the time. We'll manage. Yeah.
Yeah. Okay. Thanks. Yeah. So about the question about why there's outliers. First thing is like there are cases where if your data is small, you'd have to like find how to fit them. But aside the fact that this looks like an outlier here, even if we had 2 or 3 more points in this other side here, where this other x is, your least square, the line you get from your least square error would be in between the two of them. I don't know if you understand what I'm saying. You know, if you find the mean of these two sides, like this first side here, I don't know if you can see my mouse, and any other thing around this side here, where this last x is, your line would be in between the two of them. Does that make sense?
yeah, it makes sense.
Sorry to cut you short. Does that mean like in ab initio that the red line is actually looking like the linear regression line, right?
Yes, it's looking like it.
Thank you.
Yeah.
All right,
But
please, Mr. Stanley, before you move on,
Okay.
please, can you zoom in a bit? Like zoom it in to those slides a bit. Some persons are having issues.
Zoom in
Better.
with this slide, but I don't know about the mouse. So. Or is it better? Is it much
Yes,
better?
it is. Yes, it
Okay.
is.
So do we all understand this part? The fact that we can use this square to actually classify data, but it's best for like fitting the regression kind of data. Do you agree with this at this point? If I move on.
Yes, so my own question, sir, if I'm allowed, is
Yeah, sure.
so what is this perfect classifier that we're talking about? If you're not using this square.
Okay, yeah. So that's where we're moving towards now. Like the whole point of this is just to show you that we can't use the initial way we're using.
So are you saying we can't use least square all the time?
No, you can't use this square for classification problems. You can use it for regression problems.
Okay.
Yeah. Okay. Am I good to move on?
Sure.
Okay. So one of the loss functions or error functions you can use for classification problems are this one. So they call it 0, 1 loss. First of all, I don't know, I feel like this is a mistake here. I think you can see this less than or equals to. But how it works basically is that the output of your function is 0 if your prediction is equals to the actual data, then 1 otherwise. So basically, once it's not equals to, if your prediction is not equals to y, it should be 1, else it should be 0. So when you have something like this now, this is what it will look like. Although based on what I researched, it only be 1, it only be 0 when they're equal, else it will be 1 other places. So when you have this kind of thing now, this is an error function you can use for classification. But the issue is the fact that it's a unit step function, not just unit step, but basically a step function. So it's very discrete. And like we've said already, in order for us to perform gradient descent and machine learning, you usually have to have a continuous function that is differentiable. So this is not continuous, so we can even use this one here, this 0, 1 loss. So now alternative losses here. Okay, if you can see it here, so instead unfortunately 0, 1 loss is hard to optimize and reduce to what's called convexity function. Basically, you can get a convex function by differentiating it. I don't know if you know, basically if you differentiate a polynomial, for instance, both 2 degree or any other degree more than 2, you basically have I don't know what they call it. They call it a bell-shaped function, the curved one. So once you have that curved kind of function, you can literally find the minimum of it. So that's why your loss function has to be differentiable and continuous. Because once it's differentiable, you can find the minimum points by differentiating it and finding the value that gives that derivative 0. I think that makes sense. Well, if you can ask questions, if you have any questions at this point.
Yeah, I have a question for the student.
Yeah.
Just to juggle our memory. Can we go back to 0, 1 loss? They thought above. So what do we mean by this function not being differentiable? I want to ask you, what is the differentiation of x? Let's say we look at the x-axis at 0.
We didn't get that question.
Or what's the differentiation at 0? If you wanted to do dx equals to 0 dy, what do you think it would give you?
Q 0 because the constant.
Very close, but like, I mean, differentiation at 0 is undefined. Yeah, that's true. But what would be the different? But that was pretty close. At least you get the idea that, like, you know, you're trying to differentiate that, but differentiation at 0 at that point is undefined. But if you wanted to do the differentiation at 1, like, then you would say like it's a constant, right? Like, you know, it will be 0. So if you want to do differentiation at the negative one, there's basically where I'm getting at here is that there's no curve. There's nothing that is moving, which is the whole idea of differentiation, change, the gradient. Like you're not moving from one position to another. What is the gradient of something that is flat? That's the question.
0.
Exactly, 0. And 0, 1 loss is what? Is flat. So we cannot find the gradient. If we cannot find the gradient, the loss cannot tell us how to move. We cannot search efficiently or like on that space. So we need to find something that gives us something that is searchable. Basically, some smooth loss, something that looks like a curve that we know that if we are moving down this hill, we are actually getting somewhere, not something that is just like flat and a step like this. Does that give you like a good intuition as to why we are moving away from the 0, 1 loss, even though it's the perfect objective that we want to minimize? It tells us everything we need to know, but it's just when we need to search, it's hard. We cannot use that to search. Does that make sense?
Yes, it does.
Okay.
Yeah, so we've seen the issue with the 0, 1 loss. So here are like other alternatives to also penalizing our model. We have to find the optimal parameters. So there's the logistic loss here. So here's the function for the logistic loss function. This is the function for the logistic function. Then there's the hinge loss and there's the exponential loss. If you can see this curve here, compared to the 0,1 loss here, the 0,1 loss is basically just the flat surface, and basically we can't find any gradient of it. Compared to this other two here, which is the logistic loss, the hinge loss, and the exponential loss. So basically they are continuous and also differentiable. So they are worth using. Do you have any questions so far?
Hi, sorry, can you go back a bit? So for the for the hinge loss, yeah, that's the red line. I can see it's just a straight slope gradient, and then at one it disappears to zero.
Exactly.
So doesn't that also have effect like the 0,1 or something?
That was the question I was going to ask you. That what happens to hinge loss when it is at 1?
Yeah, we'll get to that. It's also part of it. Hinge loss has its condition, but you could actually still use it.
Yeah, whenever you're not at 1, it's differentiable. But once you get to 1, yeah, exactly. So, but it's a very common, it does not, you still differentiate it. You can still get some gradient out of it. Unlike 0,1 loss, you cannot do anything about it.
Oh, okay. All right. Thank you.
Yeah. So here is just basically an overview of the whole machine learning thing, which I guess we should be familiar with. So basically, when we create our initial model with random parameters, so we have our h of x, h theta of x, and then we have our actual values, which is y. So we need a loss function. We've mentioned a few loss functions that we consider. So basically, what we want to do is to find the loss function, is to find the value of theta that minimizes this loss. So that's the whole goal here. And we've seen so far that, first of all, we can't use least square. So this is the issue with least square here. And then we still basically have to use gradient descent to find the optimal value of our theta here. So it's still the same process in linear regression, but the point now is the fact that we're using a different loss function for classification problems. So here is still the same process whereby you find the derivative of our loss function here, because we already know at this point that it is continuous and differentiable. So when you find the gradient of it, basically we could actually find it analytically, but currently we're using gradient descent. So what we want to do initially is to find the value of theta that makes this gradient, that's the differential of this loss function, 0. So if you can see how this gradient descent algorithm works, is that we have our value of theta here that gets updated. We have this learning rate. So this learning rate is basically what guides us in our steps. So like smaller value makes smaller steps, larger value makes larger steps. Although we don't want larger steps because to make the training process overshoot. So now this is basically the derivative of our loss function here. I don't know if you can see it, but this is the derivative of our loss function. But how gradient descent works is the fact that we already know, first of all, that if we find the optimal parameter of theta, the optimal parameter is when the loss function, the gradient of the loss function is 0. So whenever we get 0 here, although in like practical cases, you don't literally get to 0, but you get something close to 0. So when you have something like that here, 0 multiplied by this, your learning rate is kind of like 0, even if it's small, but it's still 0. And then you realize that you keep getting the same value of the parameter, and that's when you got into your optimal stage. You've got into your optimal theta, rather. So that's how it's going to work. Do you have any question?
Yes, please, can you repeat what you just said about getting to 0 and all that? So I didn't get it.
Okay. And then also someone asked that is hinge loss the same as ReLU or something like that.
Hinge loss. It's kind of like the same thing, although they are for two different things. Let me see it again. Okay, the difference is you can see this is 1 minus your actual value multiplied by your predicted value. But like really it's just your data. It's not 1 minus anything, it's just max of x comma 0. But they are for two different purposes. This is a loss function. Relu is a different thing, it's an activation function. So they are two different things, two different purposes. I don't know if that makes sense. I think it's Temita that answered it, but like, did I answer your question? Like, I'm not getting any response yet. Do you have any other questions?
None for now.
Okay. Yeah, someone said I should explain this. So, like I've said initially, the whole point of this loss function is to give us an idea of how far our model is from getting the right predictions, like how far our predicted value, which is this, is from the actual value, which is y. So the simplest way which you've seen in the previous one is by just finding like difference, the actual difference. But there are many ways you can use to like penalize it. The whole point of this is to have a very large loss function when our model is very far from the when our model is far from achieving the right predictions. So that's just the whole point. Any function that gives us that, that's what we want. So now what we want to do is to find the value of theta that gives us that reduces this loss function. So that value that will make us have the minimum loss function is what we want. And we can achieve that using gradient descent. So like gradient descent algorithm, how it works is the fact that we know that because this is continuous, which is the loss function, it is continuous. So basically, if you find the gradient of it, you'd have a slope, basically. So you can literally find the minimum point by getting the derivative. So when the derivative is equals to 0, the value of theta that gives us, that makes that derivative equals to 0 is the minimum value, the minimum parameter. So those are the information we know, and gradient descent utilizes those information to find that optimal parameter. So here, from here to here, you can see this is basically the derivative of our loss function. And like I've said, we have the optimal parameter when our loss function, the derivative of our loss function is equals to 0. So we're assuming now, like let me just assume at this point that we've gotten to the theta that gives us the optimal loss function, that's the minimum loss function rather. It means this derivative here, look at this equation where theta is equal to theta minus linear rate multiplied by the derivative of your loss function. If the derivative of the loss function is equals to 0, then we'll just be having like a redundant value of theta, like theta being equals to theta. So that's an actual way of doing when you got into that optimal parameter, because the value of theta will not change. I don't know if that makes sense.
Yes, it does now.
Yeah.
Thank
you. Yes. Okay, so then we would come to examples of linear models we can use to classify classification data. So support vector machines is the first one we're going to talk about. And then the good thing about this is that we're going to talk about that hinge loss, because support vector machine uses hinge loss, and then it has this other function. I don't know if you can see it, but I can't remember from the slides if you guys spoke about regularization, or I don't know if we did. Does anyone know about regularization here? If you do, you can like just talk about it. You can just give brief.
Last week we did not discuss regularization.
You said? Sorry, I didn't hear.
We did not discuss regularization last week.
Oh, he did not. Oh, wow. Okay. Well, basically, I'll just like give you a very brief explanation of how it works. So first of all, like I said, the SVM model uses that hinge loss. The hinge loss starts from here to here, which is that math function that I already spoke about. And then it adds this regularization parameter here. So the whole point of this regularization is if our model is overfitting, and there's an actual way to know if our model is overfitting, which is when we have very large values of our parameters. So if this parameter value here, which is what you are looking for, is very, very large, it basically means our model is overfitting. So how regularization works is to add a new thing here. So not really change, like you're not really updating anything because it's the same value of theta you're using here. But the point here is that this value of theta also, in addition with this parameter here, this lambda here, we'll use it to reduce the value of our parameters in the end. So how it works is that this value here, which is our lambda here, is more like the let's say coefficient, but it's basically a value that kind of like that we use to know how much we're reducing this theta here. But in all this, basically the regularization term, the whole point of it is just to reduce the value of our theta here, so our model will overfit. So basically, regularization is just a method of handling overfitting data.
If I may also offer some intuition here. So when you think of regularization, just think about the fact that maybe you have built a model that has a lot of power, but the problem is that it's doing so well on your trained data, but once you give it a test data, it does not generalize. And the whole point of trying to find a model is like all of this machine learning point is that we want a model that can generalize to test data. So we need to find a way to balance this these two seemingly conflicting objectives, where the model is doing very well on trained data, but poorly on test data. So one of the ways we can try to account for that is by penalizing the weights, the model parameters. And that is what the overfitting, if the model overfits, that is when it is doing very, very well on trained data, but it is doing very poorly on test data. So how to circumvent that is that we will try to add a penalization, which is this regularization loss that Stanley is talking about. It just helps us to make sure that the model parameter is not overfitted. So whenever it is too large, it's going to try to reduce it by setting it to a lower value. So it's just the lambda is what makes you help you with the penalization. If you want it to be high penalization or low penalization, does that kind of give you some intuition? I know we just started talking about this week. It's usually a topic of its own, but does that give you some intuition to work with?
Hello, Pedro. I have a question.
Mm-hmm.
I'm so sorry. Quick, since we're talking about regularization with respect to support vector machine, this regularization that is being used in this support vector machine, is it going to be like an L2 or an L1? And that's my second question. Number two, you just made emphasis on regularization being, of course, we know it is to avoid overfitting, but we are just introducing ourselves to the minimum value of our in support vector machine, and we already regularizing. Are we saying that generally on the norms it's overfits? That is why we have to just regularize it. We're just straightforward. So then that's my question.
To answer your first question, yes, the regularization term that we have here is L2 regularization. We can see, I don't want to throw too many terms, but L2 is just you can see the objective there, the underscore tool. It's a way to kind of tell you that it's L2 norm, the norm there is L2. So it's an L2 regularization. If the two underscore is not there and there's no square, then you know that you're trying to regularize L1. Does that answer the first question?
Yeah, it does. I didn't understand the notations.
Yeah, I know. I know. I did not want throw into many notations so that we won't get into the weeds of it and forget the whole point of this lecture. Like you said, we are trying to introduce support vector machine very briefly, you get. And this is the general objective for support vector machine. And yes, most of the time, like it's overfit. It's not, let me try to explain myself. Because we use like kernels, we try to have multiple parameters. Like it's another topic on its own. If we wanted to introduce support vector machine as a topic, in fact, it will take a whole day, like more than that. It's a very interesting topic, but it's also one of those topics that it's heavy in math. But in general, like you might have a lot of non-linear kernels, like just to kind of like solve your problem. So you come up with these kernels that helps you transform your data in such a way that you can find a linear space to separate, like a linear hyperplane to separate your data. So in order to answer your question very quickly, those kind of like transformation can cause the model to overfit. So in order to circumvent that, again, we kind of like just penalize the model. So we have this objective with the regularization term. Of course, this is a simplistic view that I'm talking about in a simplistic view. It's much more involved sometimes than that. But does that make sense to you?
Okay, at least it does. Thank you. Thank you.
Stanley, do you want to offer more explanation? Maybe I missed something.
Okay, this is like, like you already once said, there's no point talking about regularization now. Is something to talk about later. Well, like the whole point is just to introduce us to like different kinds of models that use for classification. Support vector matching is an example of it. But I think the main thing we should just consider is the fact that we're using this loss function here. So we already mentioned certain loss functions, so that's what we're literally just going through. The issue here is the fact that support vector machines itself is built somehow, like it's built by combining this loss function here, which is the hinge loss, and your regularization term. But I think we should just leave this regularization alone. With time, I think we'll probably like get to know more about it. But the point is that if you have this as the loss function here, which is the hinge loss plus some regularization term, you can actually find the optimal parameters that gives us loss function. I think we should just put our mind away from the whole regularization thing. Or what do you think?
I agree. It's not very needed for you to understand the rest of this course. So just know that you heard about it today. If this is the first time you're hearing about it.
Yeah, and it's part of the support vector machines architecture. So
there's a question on the
same. Oh, sorry.
I said, I don't. What does penalization mean?
Do you want me to go?
You can go. Yeah, sure.
Okay. Again, penalization. Just think of it as you want to make something. Okay, I'm going to try again. So penalization of the model is just that you want to reduce the power. So like when you say you penalize someone, it's like you want to kind of like make them unhappy or like reduce their power or something. So the model is doing anyhow, is overfitting, but it's very powerful. So you're finding a way in such a way that it's still able to do it, but you want to dim their light a little. You want to reduce that power. So that's what we mean by penalizing the weight. So you're trying to reduce the size. If the weight was like 1,000, if you have a penalization term on it, maybe you're forcing it to be between some certain value, maybe come down to 10 or come down to 60 or something, depending on the lambda. I don't know if that was a terrible example.
Sorry, what is now the difference between penalization and regularization?
It's the same thing. It's regularization. It's just two different terms. Femi wants to say something.
Okay, so
okay.
the weight
Yeah, each of the way a machine learning model works is that it uses each of the weights to control the influence of each feature in your inputs. So each weight controls the influence of each feature in your inputs. So it's basically the model is basically weighting the influence of each feature. So when you're penalizing like on a weight and you're trying to reduce how influential a weight is, which is always a popular thing to do whenever, say for example, one feature is controlling the influence of the whole model. Basically, maybe the feature has a very large scale and is really influencing all the whole thing. So you can penalize the weight of that feature. You can control the influence or you can reduce the influence of that feature, especially if that feature is causing overfitting. It's making your model overfit too much on the data set. So you can reduce the influence or you can control the influence of that feature or the weight of that feature, by influencing the weight or whatever. So think of the weight as feature control,
Well,
to
thank
simplify
you.
yeah.
Sorry,
That makes
if I
sense.
may ask, this feature control that we're saying, this weight control that we're saying, is it like all this scaling, rescaling of our feature, like min, max, scalar, and all this stuff?
Yeah, it can be the first thing you'll be doing. Like it can be a pre-processing step. You can do that. Yeah, that's allowed. That way you're controlling the influence of the feature. But you can also, instead of doing that pre-processing, you can also allow your machine learning model to do it for you. Do you understand? So because when you're pre-scaling, when you're doing it in that first method, that's not adaptive to the behavior of the machine learning model when you're training in real time. But when you're using regularization, it's a kind of adapt. So you can do that first, definitely. That helps to make gradient descent work faster. So that can be your very, very first step, as a pre-processing step. But you also want to allow the model, reacts to the regularization. So in the sense that you want the model, when you are regularizing, you're telling the model, I want to be simple. I want something simple. I don't want to overfit. So the model reacts to that influence of regularization. Do you get? So you can pre-process in mixed training faster, but you can do more just by regularization to also make the model simpler. So the purposes are different. When you pre-process, you just want to make training faster and also, of course, reduce the influence of each or control the influence of each feature by scaling it down. But when you also when you regularize, you are also trying to make your model simpler. Yeah. Does that make sense?
If I understand what you are saying, let's say we want to predict hypertension patients, and we are depending on features like age, diet, and let's say the stress they undergo. So are you saying if age is contributing more to the influence, we can now bring in penalization on age as a feature? Is that
Yeah.
what you're referring to?
Yes, exactly. Yeah, exactly. The point is because maybe age is really making the model, especially if age is the biggest influencer of making the model overfit. And we don't want overfitting. We want to fit the model, but we don't want to memorize the training data. So we can use age, we can penalize and actually reduce the influence of age so that the model doesn't memorize the training data sets. The problem is that if the model simply memorizes the training data sets, it will just, like when it sees a new data set, it will just fail woefully. So we want something that's a bit more general that wouldn't fail when it sees a new data point, something simple, So we use that to control the influence of age, for example, if that was the biggest influence to why it is overfitting. Yeah, that's exactly what you mean. That's
All
exactly
right,
what I'm talking
thank you. Thank you
about.
very much.
Yeah.
Okay. Does anyone have any questions? Okay. I guess we'll just continue. So, yeah, the support vector machine algorithm uses the hinge loss, like it said, and the regularization can be mentioned. Then, just like the previous questions that we asked about this max function being differentiable. So here you can see that when you differentiate the hinge loss, we only consider the part where you have a value here. And that's when our value, which is this, is less than 1. So when it's less than 1, that's really the when it's differentiable. So that's why I would consider it only at that point here. And when you differentiate y multiplied by theta x, you'd have this, because we're literally differentiating respect to the theta. So this only happens when our value is less than or equals to 1. I don't know if this makes sense. Do you understand this? Then also you still have to differentiate the regularization term here, which is here. Do you understand this, or do you have any question? Okay, I'll just move on. So here is just basically like a plot of the support vector machine here. So we then have like this bound here, this boundary line. This boundary line is what separates them. So like already said, like in real life data, it would separate them because it's a linear model, but definitely there will still be some values that will predict rising. But the point is that we've gotten the optimal boundary that separates the two classes. Okay. Then it's basically just a plot of the like SVM model, like loss function, as we keep going down in the iteration. So the next one is logistic regression algorithm. So logistic regression algorithm just uses this logistic loss here, which you can see here. So like we've said, we already discussed, it still uses the same method which you already know, which is to find the derivative of our loss function and they use it to update the parameters of our theta. So it's basically still the same process. Yeah. So here, just like similar to our SVM model, you can have at the end of our training process, we'll have a boundary line that separates the two classes. Do you have any question? Do you all understand this side? Let me know.
Sorry, I do have a question.
Yeah, sure.
No offense, please, but if we're doing differentiation, there is this way that we know that when you're doing function of function, there is an approach. When you're doing product rule, there is an approach, or whatever it is, or when it's product. Now, on what occasion can we or do we put logistic regression over SVM? And
Sorry,
in what situation or occasion is SVM a better option to logistic regression, and in what situation is logistic regression a better performer to SVM? Or we are just saying they do the same thing. So if they do the same thing, why one over the other? Why do we have a second one?
Like this, like if you see the architecture of SVM, which is the only thing I know, is the fact that you already have a regularization thing. So the SVM model would be less prone to overfitting. That's the only difference I know personally. But based on the whole point of what it's trying to achieve, it's basically just creating a line that separates both of them. If I was to like do a classification task, there are many other ways you could use. You could use neural networks, you could use this, but these are just like linear ways. So they kind of like, they're very similar. And I think their outputs will be too different, except for the fact that you might have better performance on your test data with an SVM because regularization term compared to your logistic one. But I think you could still add your regularization term to your logistic function too. But that's it for me. Or except if do you have anything, any other reason or Femi?
No, I didn't catch all of the question, unfortunately. Sorry.
Oh, okay. The question is basically, is there any reason why you choose SVM over logistic regression, or the other way around?
Oh, no. It's just they're optimizing different objective functions, and you can always just use the different ones and decide which one works best. But for small data samples, like you might want to use SVM. But like if your data is like very, 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 very large and in the millions, then SVM might not be the best because of this kernel, like constructing, you're always constructing new features, and that is in the order of the number of samples that you have. So that you might want to favor logistic loss for that one. But that's the only reason I'm thinking of right now. But other than that, it's usually just like preference, so to say.
Okay. Okay, do we still have any other question, or did that make sense?
Sure.
Okay. So this still the same thing, run it on a master data set. So basically still the same process. We get our bounding box that separates them together. Then, yeah, at this point in time, so basically what we've been going through is just a binary classification, whereby we just have two data. But there are many other cases where you want to classify multiple classes. So that's where this multi-class classification comes in. So you might want to predict like an animal, if it's a dog, a cat, a goat, or any other thing, you might want to predict some other things too that are classification problems for multiple classes. So there are two approaches to which you can do it here. So the first one here is by building classifiers for each of the classes you want. So there's what they call one versus all, that kind of thing. So how it works is that you build the classifier to identify just a single thing compared to any other thing, but you do the same thing for each of your classes. So it's more like you build a classifier for the first model to predict, for it to be able to predict just that class. Then you do the same thing for every other class. Well, as you can see it already, like it's kind of like more stressful and more expensive to even do such. So the second approach here is by using what they call like softmax. So softmax is similar to our logistic loss, which you already saw. But the point now is that it's not just for two things, which is binary. Like what softmax does is that it kind of like groups everything. So if you are predicting something between 0 and 1, for instance, softmax kind of like makes everything sum up to 1. So if you're predicting that for, I'll just say like 3 animals, like if the animal is a dog, a cat, or a goat, softmax merges each of them into just a probability of 1. So you won't have any value going outside of that range, 0 and 1. So that's why they use softmax for that. So in the end, when you make your prediction, softmax gives you the probability of it. So for instance, you could have something like the probability of it being a dog being 0.2, that it being a cat being 0.3, and it being a goat being 0.5. So at that point, you can then decide what you want to do with those probabilities. You can decide to like say, okay, since it's the highest probability, which is good, I can say my classification is good. But realize that now you are making your prediction for multiple classes. If you have like 10 classes, all of them will still sum up to 1. So that's how those softmax work. If you have any questions, I'll be confused about anything. Yeah.
Just can you come again on the soft class?
Okay. So we all know like how that logistic one, or more like a sigmoid function, works. In the fact that how it works is that since it's binary classification, we are just predicting for just two things. In this first approach, like I said so far, if you want to predict for multiple classes, like just repeat this one, you build like you make predictions for each of the outputs individually. So it is more like you're predicting for one class versus every other thing. So your model knows how to identify just one out of those classes in the number of forms that you want. But like how this softmax function works is that all your predictions they are going to give would sum up to 1. So this time around, you're getting probabilities for each of those classes. So if you have like 5 classes, those 5 classes must sum up to 1. Even if the first one is 0.0, the first 4 are 0.1, the last one is 0.6. So softmax kind of like makes everything sum up to 1. At that point, you can know the probability of each classes. that you have at that point. So you can then like equally say the one with the highest probability or the one with the highest value is the actual one that is predicting. Like if you're still confused, you can let me know. Let me see if I can see like an image or something to explain it. Very sense. But like, do you understand how the stock market works?
I'm not sure many of us understand yet.
Okay, let me see. Okay, let's be a minute now. Let me see. So let's just say you want to predict two classes. You want to predict two classes. There's a popular like value that they use for I don't know if you've heard of sigmoid function, but what it does is that we use sigmoid for like two classes. Basically, it finds the probability of two classes. If we're doing binary classification now, it finds the probability of either of the two classes. But the point now is that because we know that it's binary, we can easily just find the highest between the two of them. I don't know if you get. So let's just say the sigmoid function is between 0 and 1, for instance. But any value in that space, any like class, they can have probabilities of it being whatever it is. So let's just say we want to predict two classes, like if an animal is a dog or a cat. The probability of it being a cat can be 0.7, and the probability of it being a dog can be 0.8. At that point, that's just like the probability of it being any of those two.
Sorry, can't hear anything now.
I think we lost Stanley.
Yeah, it was talking about picking the one with the highest probability for our decision, right?
Yes.
I think someone is not asking, what about the situation when we have equal probability? Like the same way it can be a cat, it could also be a goat.
Oh, yeah, then we just have to decide the decision whether or not, like, if the probability is that it's equal across both class, you just have to choose one class. Usually you have if probability is greater than or equals to. So in this case, that scenario will fall into the equals to. Do you understand what I'm trying to say?
No, I don't
Yeah,
Is
understand.
that
one
not
right now.
reducing the efficiency of the
I
model?
mean, you have to make that try. So let's say you're making a decision for sigmoid function, for example. You're going to say that if, let's say, y is what we have named the variable as, if y is greater than or equals to 0.5, then classify it as class 1. Otherwise, class 0. You wouldn't say if y is greater than or equals to 0.5, get it to class 1. If y is less than or equals to 0.5. You understand what I'm trying to say?
I get now.
Yeah, somehow you still set the threshold, and then the one that has the equality bound would push the like whatever value whenever you have those kind of scenario where you have the exact threshold being met.
Okay, thank you.
Just to clarify, would that not cause a bit of biasness as we're favoring one class more than the other for an equal?
We always hope that your model can know with confidence, like more than 0.5, to put it in one class. But if your model is nothing more than like it's just randomly guessing, there's not much you can do, right? Like you probably need to train a better model, or get more data or something. But even for you yourself, that's not a good decision. Like you're literally just trying to do this one or that one, age or UJ. But you're right. There's always some form of bias in your model, and there's some form of variance in your model. So all of those things, you cannot completely make them zero. You
Yeah,
have to
then
trade.
sometimes so like if you have more class than the other, you might have to like set a lower bound, a listen, lower threshold or some things. Okay.
Can you explain that again? The lower threshold part.
Although that thing is a whole topic on its own, but sometimes now if you're doing like a binary classification, unfortunately you might have like one class being more than the other class. Like I mean with the way the data is being generated, like one class can be lower. So your model might learn more from the other class. I don't know if that makes sense.
Yeah.
Yeah. So sometimes like that's why some people use threshold. There's what they call like all these false positive, false negative things. Like that's exactly what they use for the threshold. Sometimes it's not just accuracy you are looking for. Sometimes you might want to have, okay, for instance, I'll give an example. Like I think it's PayPal, but they would rather, I think they use an AI model to predict fraudulent transactions in their system. So even if once they detect any form of fraudulent activities, even if it's not fraudulent, they would categorize it as fraudulent. You get, so like they have let me see, I think they put a lower threshold for, let's just say we're saying fraudulent acts are one rather, and then non-fraudulent transaction is 0. So they'll put it very low, rather they'll put it very high. No, rather they'll put it very low. If fraudulent transactions is 1 and the non-fraudulent transaction is 0, they'll make the threshold very, very low. The reason why they're making it very, very low is so that they will be able to catch anything that is even close to being fraudulent. I don't know if you get what I'm saying. So they would rather have you like go through their process of verification than to allow a fraudulent activity. Does that make sense?
Okay, that's like, sorry to so that's like PayPal saying any transaction that has to do with a Nigerian, flag it. Let us manually.
Well, not necessarily Nigerian, but like
yeah, I know. I'm just assuming.
Okay.
So like, okay, once you see Nigeria in it, you want to flag it and say, okay, manually go through it and ensure this thing is not fraudulent.
Something like that, for instance.
Yeah.
But yeah, in terms of that threshold things, let's just say the binary thing, let's say between 0 and 1. So you set the threshold to something close to 0, not necessarily like very close, but something that would catch anything like that is very close, even if it's very, very close to fraudulent, because we'd rather have it see a fraudulent activity, a non-fraudulent activity as fraudulent, than for it to see a what do you call it, a non-fraudulent activity as fraudulent. Let me see. They rather have you see, they rather accept a non-fraudulent activity as fraudulent than to mistakenly take a fraudulent activity as non-fraudulent. I didn't get what I'm saying. So it would be very, very bad if something that is fraudulent, their model classifies it as non-fraudulent. So it has more effect on their company as a whole. So yeah, that's like some cases where people set thresholds in their model. Okay. So I think like literally, I think that's the end of it for the whole theory side of this. I don't know if you have any questions, please, I'll let you know. So I think someone asked a question. Okay. Oh yeah, yeah. So I think Sharon explained it already on the chat about having like balanced data.
Okay.
Okay.
Yeah, in the area of balancing data also, there was a project I did recently with Smooth that was generating synthetic data, so that's just to balance the data, and I realized that it was it was overfitting the data based on the synthetic data generated, because it was performing well on a section of the data, but very poorly on other sessions.
You said you balance the data, right? You said you did that.
Yes, I try to use Smooth to balance the data. Smooth.
Okay, okay. Um, but you said it started performing bad on one of them after you used Smart.
Like my F1 score from my own laptop was very good. I was having 0.9, or when I actually tested it on new data, it dropped really bad. I think it was dropping to like 0.5 and all. And when I inquired from someone, they said it was because the synthetic data generated was kind of too much. So it was giving some bias to the model.
Oh boy, I thought you said you already like balanced it already.
Yeah. I
What?
think I get what he's trying to say. Like if I understand correctly, you use mode to use computer that noise is coming from. Oh, Sharon, do you want to offer some explanation?
Yeah, I wanted to explain that machine learning is something that you keep trying different methods, right, to get what works best for you. And then again, smooth is something that you use to balance your data, but it's not good when you have, for example, if you have 6,000 samples, total data samples, and then a class is about 4,500 or about 5,000, and you have another class of just 1,000 samples. So if you make use of smooth, it's going to like you're going to have more synthetic data than actual data, and that would affect the performance of your model. So personally, for me, in times like that, I rather like reduce a little bit of the class with more samples. That's if I cannot get more data having other samples. So you have to like reduce a little and then apply smooth so that there's relatively a similar or a closer range between the two classes. And secondly, another thing with model development is that there are some type of models that are too perfect. For example, decision trees, right? So you make use of very good models on simple data sets, right? They are going to there are high chances of them overfitting your data because they are complex models and your data is not as complex as the model that you're making use of. So at the end of the day, you're having something that results to a perfect solution. And when you apply them to real life, they don't perform as well as you think they do. And secondly, your validation data. You also have to ensure that your model, there was no leakage, right? So you have to ensure that the validation data has never been seen by the model, and the evaluation you're getting out of your validation data is actually accurate and not something that been leaked, and your model is just giving you back what you want to see, and then when you take it out there or when you use it on entirely new samples, you realize that your model is not as good as you think it should be or it ought to be. So I think that's what happened in this situation.
Yeah, so like the thing is that there are many things that are, when I put it, they are still vague in the whole machine learning thing. But first of all, personally, I won't like really recommend the whole downsampling or upsampling of data. So for instance, I don't know, for those that don't understand, I can explain it. So upsampling your data means like the data with less class, with less data, there's the class with less data, you like step it up. So you'd have equal classes of that lesser data being the same with that of the higher class. I think if that makes sense. Well, downsampling means reducing the higher class, that's the class with higher data, down towards the class with lower data. So that's the way that people recommend. But the thing is that they have their issues. Like upsampling can give you like wrong data that you might not even see when you're testing or in production. Well, downsampling can reduce the amount of data you have. So for instance, if the majority class like has about 8,000 and then the minority class has about 100. So when you downsample rather, you'll have 100 for each, which will most likely make you overfit depending on the kind of data. So like there are many issues associated with this. There's a way that is recommended, which is like actually adding a factor. I would still use the word penalizing, but penalizing your upper class in your actual loss function this time around. So when you're building your model, you penalize the majority class so that the minority class can learn more. I think that makes sense. But that's an approach for it. Then also some other things to note before you like do the whole down sampling and up sampling thing during machine learning development is to actually know what your production or test data would be like. So there was a case whereby like we were working on a project and there was obviously a majority class and there was a minority class. So once you have something like that, the model will learn more from the majority class. Then we try to upsample rather than downsample, use the whole smooth thing, assign weights to the lower class and all. So it would learn each of them equally. So when that same model gets to production, for instance, and then in production, we still have the same thing, like the same distribution that I just mentioned, where you'd be having more of the majority class and minority class. In that kind of case, it might start performing like bad because it's trying to treat two of them equally. So the thing is to know what your test data. In fact, that's what the whole point of test data is. So you can know how to perform outside. So you need to like make sure that they're kind of like in sync. I don't know if that makes sense. But that's like based off my experience, and that's what I recommend. So
Jerry has a question, but before we continue, I quickly want to make an announcement, if that's okay. Stanley, would you still like to be on the call, or do you need
yeah,
to?
sure.
Okay. Yeah, I'll quickly just share my screen to do that. First of all, thank you so much for the class. I think we've officially finished the class, right?
Yeah.
But we still have some question which would like to continue the conversation. So we have a deadline for the practical session, which is we've released practical notebooks 1, 2, and 3. And there is a deadline for this Sunday, not this Sunday, sorry, next week Sunday, which I cannot remember the date, but I'll put it in my recap later, recap notes. So next week Sunday, end of day is the deadline to submit practical 1, 2, and 3. And it's really important that you do that practical notebooks, because if you don't do it, then you would not be eligible for a certificate. And just to give you a sense of where we are right now, we've been going through topics like we've done introduction to data science, data collection and scraping, relational data. We've done visualization and data exploration. We've talked about matrices, vectors, and linear algebra. We did data preprocessing. We did introduction to machine learning. And today, we've done linear models. So we are already far off in the cohorts. Next week, we're taking a break. So there's no class next week. And that's why we hope that you can use the time to catch up with your practical session, practical task 1, 2, and 3. On Sunday is the deadline. Please make sure to work on it and submit, because I mean, even though you attend all of the classes and you don't do all of this practical, you don't meet up with the requirements for certificate, we won't be able to issue one for you, and that would make us really sad because you attended all the classes. Again, if you're not very clear, try to read this document just to understand where you are and how you might ensure that you get all of the requirements that we need. So that's the announcement I have. We can continue the question.
Sir, the break, does it extend to the practicals too? You don't have practical class next week?
There's no practical session next week. There is a break. We are completely on break. And when we come back on 6th of November, we will continue with machine learning.
Thank you for the break.
Yes. You're welcome.
Yeah. Sorry, I have a question on the
announcements.
Okay.
Okay, just to briefly answer the announcement, then we'll get your question. I will be later today or tomorrow. I'll be releasing a leaderboard that shows the performance of the different teams so far, so you guys can really understand how bad you're doing as a team or how well you're doing as a team, compared to other teams. I'm hoping that this should be a form of encouragement to ensure that everyone is working together, like as a team, and trying to really, really help themselves out. The purpose of this whole team thing is to really give you this sense of like supporting others, to give you the opportunity to learn to support others and to also get support along the way, So I'll be doing that very soon. I'm currently working on that, but I'll be releasing it very soon so you all can see how you're performing so far, compared to other teams. Yeah.
Thank you, Femi.
I think Jerry has been raising his hand.
Any question? Okay, please go ahead, Jerry. I think he has a question related to the class.
Okay, yeah, thank you. All right, so I'm kind of new to machine learning, so I'm trying to get a grip on what we are trying to discuss here. So last week what we are trying to do is, okay, so we have this continuous set of data, and then we want to be able to build, we want to be able to get a linear equation, a linear line that we can always use to predict what will happen if we have one side of the parameter and want to get the other. Want to get what should be the other side of the parameter. So last week, it was more of peak period and temperature. So maybe I have temperature, I want to know what the peak is going to be like and all that. So today, the thing is, I'm kind of confused what we are trying to. Today, is it like we are just saying, okay, we want to know if this person has breast cancer or does not have breast cancer? Is that what we are trying to do? And how does because I just saw a lot of equations, a lot of mathematics. So what we are trying to do basically today is just the same thing like last week, except that we are just trying to separate and say, okay, today we have cat and dog. We want to be able to ensure that our machine model can easily predict that, okay, anything that falls here is a cat, anything that falls on the other side of the line is a dog. Is that what we are trying to do? Just in summary, that's just what I want to know.
Okay. The thing is that, like, based on your explanation, like, you actually like have an idea of exactly what we're doing. There's something similar between what we did now and what we did in the last class. The point is there isn't just a line to like know your points, to like know how good your model is. So in the last one now, if you notice the kind of data we're giving data that are kind of like continuous and data that you can't literally like discretely say this is different from this. For instance, 1 and 2, or there could be multiple. There could be a cup, a mouse, a like laptop, that kind of thing. But you're having things like values, for instance. I'll give you an instance, predicting house pricing. Like house pricing can be any value, not necessarily discrete values. This time around, they're trying to like classify discrete kind of things. The similarity between two of them is the fact that we are using a line to like know to make those predictions. But in the last one, your line is for fitting that data. Like even a set of data on a graph, for instance, you're using a line to know the line that fits each of them, that fits all the data points. While in this one, your line is just going to be a separator. So it's like a boundary. So this time around, your line is not going to fit any data, but it's going to like tell you that anything in this region, which is greater than that line, belongs to a class. Anything in another region belongs to another class. So that's the difference between two of them. But they still follow the same procedure of machine learning, which is initially like having initial values for your model, then creating a loss function. That loss function is what tells you how far your model prediction is from the actual one. And then finally optimizing, like finding the parameters that gives you either that line of best fit or the line that separates classes together from each other rather. I don't know if that makes sense, but
Yeah,
that's exactly the
yes,
explanation.
Jerry, what you said is exactly correct. That this week we are the example task was to predict whether or not a sample is the breast cancer. We want to predict whether or not it is benign or malignant. Benign or malignant. That was the task for this week, and it's a classification task because we are either saying either this class or this other task. Does that make sense to you?
Yeah, it does. It does. I understand that concept. It's just the whole line movement, like for last week, we were able to say, okay, this line is not a fit, and then we are adjusting and adjusting to it. So, okay, now we have something that looks like we can easily predict. Now, this one, a cat will always be a cat, a dog will always be a dog. Now, if you look at the first set of graph in this lecture, we have a line that separates. On one side, we see have some red, and on the other side, we see have some blue. So where do we say, okay, now our own line here is perfect, because that means we are still going to be having a lot of guys that we classify as benign cancer, whereas they have malignant cancer, and vice versa. So that's the whole adjustment today is since there's no way, we can't have a straight line that is going to decide this. We can't have a straight line. So at what point do we say, okay, this model is perfect to predict whether somebody has a benign cancer? I don't know. I guess I'm just misyanning.
Yeah, you're right. You're right. It's an artifact of your data. And let's say the example was, I agree, it's a very complicated example. But the thing you should understand, it's not that complicated. So what we are looking at right now is just two features, which is the mean concave point and the mean area. Naturally, you wouldn't be using just two features to do your train your model. In this data set that we talked about, it has over 30 features. But because we wanted to plot it, we are just looking at two features. And these two features already is a good predictor for whether or not the cancer is benign or malignant. But to answer your question, in the general spectrum, if you're using these 30 features, it's possible that you would find a line that's multiple hyperplanes, so to say, that's perfectly is able to help you classify whether this is benign or malignant. Of course, not like perfectly. You still have some level of error, but you definitely do better than maybe just using two features if the rest of the features are really good predictors. Does that answer your question?
Yeah, it does. Thank you.
Okay. You're very welcome. Do you have any other question? So to conclude today's class, I also wanted to mention that since we're having a break next week, the whole point of the break is to help you breathe and catch up with your past lecture. And again, your go-to for this cohort is this page, because it has all the things you need to stay in check. So if you want to watch the previous classes, you can just go to this YouTube playlist, and then you can see all of the classes we've held so far. I'm going to add to this class here. You can look at all of the class to catch up. If you want to look at the practicals, go to this YouTube channel and you can find all the practicals we've worked on so far. If you want to look at the repository that each of the instructor uses, they present their material, they usually put their work under this repository. You can catch up with that. Ditto, if you wanted to look at your practical repository, you can catch up with all of the practicals as well. So we're just trying to make it easier for you to navigate information and find information. So try to use it. And if you find some bugs or something, you can edit it, add something new, maybe some resources, not like resources, we have another page, but if you want to add something like contribute to this page, you can contribute and send PR and we'll be happy to review it. So so that's it, guys, for that front. And without further ado,
I checked this morning and I did not see the materials for today's practical.
It's there now. I meshed it this just maybe after you checked it. So this is it.
I think it comes later because I was hoping to prepare and download the necessary before practical session.
Okay, apologies for that. I do agree that I reviewed it earlier this morning, but that is not Tunde's fault because he sent it to me like in the middle of the night. So we'll try to make it available maybe before the class, maybe a couple of hours. I don't want to make any promises. So yeah, but we'll try.
All right, thank you.
All right, okay, thank you so much. But it's there now, you can already catch up. We'll have a longer break today because we finished early. So we'll come back at 12 o'clock to start the practical session. So you can take the time to set up your laptop and look at the slides already. Do we have another question? So please, everyone, help me say a warm, big thank you to Stanley. It's about 4 a.m. your time, right, Stanley?
Yeah, thanks.
Oh my God, and you still answered all of the questions. He's probably sleepy right now. So thank you so much for joining us today. I really do appreciate it, and we all really do appreciate it. So please just everyone shout out, say thank you to him on Slack or on, anywhere you want here. Just thank you so much. Yeah.